So last class we finished the Average theorem, right? So this class we're gonna do some extra material with regard to the Average theorem. So one thing I want to close today is an extension to what happens when you have a lack of indifference. So we have demand functions. Okay. So we're gonna strengthen the GARP, the generalized axiom of real preference, and we're gonna do it for with the following condition, which is called the SARP, as I mentioned. So the real preference relation is acyclic. That means if XD is indirectly real preferred to XS, any two observations in a finite data set, then it is not the case that XS is directly real preferred to XD. So what is the difference with GARP? Well, the only difference is that in GARP, here we require that this part is a strict direct real preference, right? While in SARP, it's just a weak one. So in this case, this is also ruling out indifference, right? So in other words, the SARP is a condition that works when there is only demand functions, right? Singletons, okay? Agree? So that's it. Now, so I'm just gonna state the theorem. It's very simple. The theorem says there exists a continuous non-satiated utility function U that is strictly concave that rationalizes the data in the sense that for all k, U of k is strictly greater than U of x for all x different from xk, such that pk times xk greater than or equal to pk times x. So the same as the previous theorem. What is the difference? Well, there's two differences. First is strictly concave instead of concavity. So remember that with strict concavity, you get uniqueness of the demand function, right? So the uniqueness of the demand function is essentially the new thing you get, and this is the byproduct of strict concavity, okay? And the second thing is this thing here, there is a strict greater than equal because this is the only maximum, right? So xk is a unique maximizer, so it has to be strictly above the rest. There is no indifference at the top, okay? So the second condition, which is equivalent, is that the data set satisfies the SARP, okay? The strong axiom. And the solutions of the Afred inequalities are similar, but here instead of having a weak inequality, you have a strong inequality, okay? So I'm not gonna prove it because the proof is exactly analogous to the GARP, except that there are some tricks that you have to add some wedge such that you're able to get a strict inequality, right? So a full proof of the strong axiom, you know, that's beyond the class. So it's too technical and it gives you just this special case. What I'm teaching you is that in the old literature, especially Mas-Colel, he focuses on the SARP instead of the GARP, right? And the reason is that in Mas-Colel, mainly the focus of the study was demand functions, right? So there is this little section where he talks about Hutaker's condition, which is SARP, and he says, you know, this is the one that is equivalent to rationality. So yes, this is equivalent to rationality essentially when you have demand functions instead of demand correspondences, okay? And then, of course, the more modern approach is the GARP, right? The generalized axiom of real preference. So the previous theorem that we proved. Now, so this is just, again, kind of a historical link with Mas-Colel. Now, forecasting. So what do you do besides testing? So you have a data set, and this data set will be rational or not, right? And now the variance supporting set is essentially a way to be able to do something that's called forecasting. So what is forecasting? Forecasting means that you have a data set, and now you have a new price and a new, of course, income. Then at this new budget, what would be the new demand possible? So when you have a model of behavior, and then, for instance, from data, say you use traditional econometrics to estimate a demand function, then what you would like to do with this demand function? You would like it to use for many things. One of them will be prediction, right? So at a new point, a new budget, you would like to predict the demand, okay? So this is called a counterfactual demand question. So here, essentially, I'm doing that. So I'm asking, this new budget, which is given by price K plus 1, and also an income K plus 1, I'm asking, what is the demand bundle that is compatible with the model? What is the model? Utility maximization. Now, how do I ask that without knowing the utility? Well, you don't need to know the utility because you know that the original data has to satisfy GARP, right? And if there is any non-parametric utility that also is able to generate the out of sample data, then basically GARP has to hold in an extended data, okay? So O union PK plus 1 comma X, right? That means O is the original data, and then you are augmenting the data with a one additional row. The new row has a new price, PK plus 1, and then X is the unknown variable, so the demand you want to predict. So basically, this set is describing all X's, all vectors that satisfy GARP in the extended data, right? And such that the multiplication of the new price times the new bundle is equal to the target income. Do you understand what this is doing? So essentially, remember what is GARP doing, right? So GARP ensures that there is a utility maximization generating the data, right? So basically, for this set of X, right, is essentially the set of all alternatives or bundles, right, that are generated by some utility function, right? And this utility function also happens to generate the original data, okay? So in that sense, it's a counterfactual prediction, okay? Importantly, right, this utility function will generate the original data, okay? Rationalize the original data, okay? So yeah, so besides defining this, then the rest is super simple, right? There's the set of demand observations that given the new price level PK plus 1 is such that GARP still holds in the extended data set, right? Then X belongs to the supporting data set, PKWK plus 1. If PK plus 1 is times X is less than PK plus 1 times XT, and for all such cases that XT is strictly will prefer to X, and PK plus 1 times X is equal to the income level. So in other words, this additional condition ensures, right, that given a real preference relation that satisfies GARP, this condition 1 and 2 is enough to characterize the whole set, right? And this set is called the variance supporting set. So in other words, this thing here is predicting the set of all alternatives that are compatible with utility maximization, conditional that the data is the original calligraphic O, okay? So what this is telling you, this is very cool because it is a non-parametric way of doing demand analysis, okay? It's a non-parametric way of doing demand prediction. Okay, so any questions here? This is kind of mathematically simple, but conceptually it is kind of hard. So let me know if you have any questions. No? Okay, I will keep going. So now we're gonna do upper bounds to welfare analysis, right? So in this particular case, we're gonna say that you also, if you have a model of demand, you would like to do welfare analysis, right? So to analyze whether consumers are better off. So one key object for doing welfare analysis is something called the money metric utility function, right? So the money metric utility function n of px is equal to the expenditure function evaluated at some price, and then instead of the utility, you just replace the utility evaluated at the x value. So in other words, this money metric utility changes the units of the utility that is in arbitrary utils, if you want, but arbitrary units, and then changes it to dollars, right? And by which means? By means of the expenditure function, right? So the expenditure function, remember that is measuring dollars. So once you fix a price, this is very important, right? These are going to give you dollars with respect to that particular price. So when you evaluate this, any utility, it's going to give you back dollars. So this is called a money metric utility function. So this is good because this money metric utility function can be used to do welfare analysis that has some meaningful units, right? So again, a mass color is a bit weird because in general, welfare analysis is a bit weird because until this point, everything has been ordinal, right? So we only care things that maximize, things that are first, rankings, you know. But now, since we have utilities, since we have linear budgets, since people are spending money, now we can talk a little bit about units, right? So in particular here, we're gonna measure changes in welfare in dollars, right? So which is a cardinal analysis. So when you do welfare, you know, usually people go back to doing cardinal analysis, and we're gonna think when this makes sense. But so in particular, in this case, we're just gonna introduce this object, and then we're gonna study it a bit more later. But remember that expenditure function is just the result of minimizing the expenditure subject to this u of x is equal to u, so the target utility. Now, for any given price, the m of px is a utility function that represents the same preference u, but is expressed in money units, right? Now, given a finite data set O, Varian suggested an upper bound for the money metric utility. So using just the reveal preference relation, you can actually create an upper bound for the changes in welfare. So this is called M plus, and in particular, you can minimize, given the price, you can basically minimize across all observations xt, such that xt is reveal preferred to x, right? And if you do this operation, right, given R is your data, right? It's the reveal preference relation, then you will obtain an upper bound of the money metric. So in particular, this will give you, the maximum change in welfare that the consumer has. Now you can also do a lower bound, right? So it's very easy to define. You can basically, instead of using the xt superior to R, you can also try to instead maximize, but instead of on the lower contour set. So I'm not gonna do this here because that's not the objective. The only objective here is that show you that with real preference, you can, for instance, know the maximum possible change of welfare that a consumer can have without knowing the actual utility. So because we don't know the actual utility, this is just an upper bound, right? You cannot point it out exactly. And yeah, so usually the lower bound is not very informative, so we don't care much about it. So this is the second object that I wanted to introduce. Okay, so now, previously, in other classes, now I'm gonna switch to some experiments about rationality. But now, a lot of the work here of this experiment is gonna be done by you in the problem set, right? So remember that you have to implement the GARP for this experimental data set, right? So there is several data sets right now that have some tests for rationality. I'm gonna describe the experiment more in this class so you understand a little bit also of course you have the data set and you can implement the GARP, but a little bit understand more what kind of experiments people are using, right? So in the end, I couldn't fix this thing of the figure. It's irrelevant for the class, so don't worry about it. The only thing that I'm going to describe right now is the following experiment, right? That is the prelude to the experiment that you're using. So the one you're using is a follow-up paper of this thing. So this is the original experiment, okay? The one that we're going to study today. And the one you're going to use in the problem set is a follow-up of the original experiment. So this is an experiment for consumer choice. Originally, what they're doing is essentially they're doing a portfolio choice experiment. So it's kind of a fake investment experiment. In particular, they only provide 2 states of the world, right? And each of state of the world has a known probability. And then they sell Arrow securities. What is an Arrow security? It's a contract. So you can buy dollars of that contract. That is a promise that if a state of the world one happens, then you get that money in that state of the world. So it's sort of a kind of an insurance. That's called an Arrow security. So if a state of the world 2 happens, then it also pays you some amount. So basically you can buy these promises for state 1 and state 2, and they correspond to a bundle, right? What is the number of goods here? 2, because there are 2 states. And essentially you can buy any fraction or promise of money. So you can buy this asset in any fractional way you want. So the whole choice space is RL, where L is equal to 2. So this can be described. So the choice from this can be described through means of a budget constraint. So the budget constraint will be determined by the price of this promised dollar in each state of the world. So it's the cost of the insurance. So there's going to be P1, P2. And then, of course, the income or wealth level in this experiment is always going to be fixed to 1, okay? So it's always 1 or 100, but it's always fixed. So now with this in hand, what these experimenters do is they show the problem to the consumers, the subjects, the experimental subjects, by means of a linear budget. So they actually give a computer screen, where they draw a budget line, like the one you see in the Mas-Colel book, right? So they actually draw a budget line. And then they ask you that with a mouse, a pointer, right? You pick over the budget line, okay? And then the choice that you put, and they don't allow you to choose things not on the budget line. So they are forcing you to choose, the just on the frontier of the budget line problem. So this problem is just choosing in the budget line. However, they present to you, the whole ORTAN. And then you can use the mouse to choose any position you want. So the position you want, of course, is a point in the ORTAN, which is a vector, right? And this vector describes the quantities of Arrow security of state 1 and state 2 that you want. So in particular, this is a commodity band. So what they use in this experiment, they use 93 undergraduate subjects that participated in the experiment at UC Berkeley, right? This is very common, especially it was very common in the experimental literature. So they use a lot of undergrads, similar to psychology, right? As opposed to psychology, so in psychology, people usually force their students to participate. So they pay them kind of credits or whatever, but they usually have to satisfy certain credits in order to become a psychologist. So they are kind of forced. But in economics, we always pay them actual money, right? So it's always voluntary. So in this particular case, the recruitment is done through public announcements. And then they say, this is the show-up fee, and there is a participation fee that depends on the performance, right? Because this is an Arrow degree security, you actually have a computer to run the probability that each state of the world happens. And then essentially when you do that, and the states of the world here are 1/3 and 2/3 and 1/2, 1/2, if they have treatment and control for that, they run these probabilities, the state is realized, and then they are paid according to this insurance, right? So they receive the money according to that. I'm going to describe the payment scheme in a second. But right now, the important thing is that people will show up, they get paid for showing up. Then they participate in 50 decision problems, right? So why so many? Well, the whole innovation of this paper that was published in the American Economic Review, AER 2017, was that they were the first allowing experimenters to have many decision tasks. So usually, if you remember, this is one innovation of using computers in experimental economics, right? Before, if you were asking them, what do you want to choose? You'll have to give them kind of a piece of paper, right? And in this piece of paper, you have to ask them different options, right? So bundle 1, bundle 2. So describing all options in a budget line is very hard, right? So these guys, they say, no, let's do instead this graphical visualization. They can use the mouse, they can point and click, and now you're gonna get randomly a new budget. You're gonna point and click. So this can be done very easily, right? Instead of presenting a list of alternatives, you can just see the budget line, the graphical representation, and interacting with the visual interface, you'll be able to choose very quickly. So that was their innovation, and that means they could actually run many choice tasks. So this is one of the experiments that has the most choice task. Is 50, is a lot, right? So remember that, for instance, when we in economics, we were starting, right, as science, the only data set we had was time series data from countries, right? Like the aggregate consumption of countries. And usually, you know, when you use this time series data, it was great to have, you know, for a country without structural breaks, you know, 30 to 50 observations, right? That was amazing. So now, you know, you can actually get from each individual 50 observations, okay? So that's pretty cool. Now, again, the design was that there were two states of the world, and then they have known probabilities. In each decision problem, every subject was given a budget, income was normalized to 1, and instead prices were chosen at random. So each new budget was generated at random by the computer. Then 47 subjects, almost half of them, were subject to the symmetric treatment, where the probabilities of the state of the world were 1/2, and the rest had the asymmetric treatment, when the probabilities went 1/3 to 1/3. Okay. Now, so that's the problem. Now, if you have 50 choices from budgets, that means that our data set that we discussed before, right, was of size 50. Okay. So you have 50 vectors of prices. Each price is a vector of size 2. Each commodity bundle is a vector of size 2. So in this setup, you can test GARP, right? So now people test GARP here. And then what do you get? You get that in the symmetric treatment, 12 out of 47 pass. In the asymmetric treatment, 4 out of 47 pass. Roughly 17% people, undergraduate subjects in Berkeley, pass the GARP. Okay. So again, GARP is super simple to test. You take a data set, you pass it through the program to test GARP. Basically, GARP is checking that there is no these violations of the strong cycles of the real preference, right? And that's it. Now, if you do this, 17% of people pass. So that's of course a big shock. You know, irrationality is a good theory of behavior. It should describe, you know, essentially, if we're super serious about science, it should describe everyone, right? Because we are assuming as economists that everyone is rational. Okay. But you can argue, okay, great. We know maybe economics is not claiming everyone is rational, but most people are rational, right? Okay, well, it's most, well, certainly is not 17%, right? So certainly is not 17%. So what's up? So what do you think, you know, what do you make out of this result? Opinions here?
Maybe there's something wrong with the data, like it doesn't reflect, yeah, it doesn't really capture what we're trying to get at.
Okay, that's a good point, Amat. Can you expand a little bit? So what do you say it doesn't capture what we want? So what do you think ideally we would like to have as economists from an experiment of choice?
I'm not sure. I mean, I can't think of something off the top of my head, but I'm just thinking that, you know, maybe the way that they ran the experiment was faulty, and that's why they only got 17%, because the conclusion just doesn't make sense. As you said, if this was in physics, we would disregard this right away.
Yeah. So this is a tricky question, right? For instance, what does it mean to run a proper experiment? These guys, you know, they published their experiment in the American Economic Review. So that means, you know, this is one of the top 5 paper journals. So there has to be a lot of filters, right? So they are serious researchers, you know, they they paid properly the subjects. Subjects are not crazy guys. They are undergrads from one of the best schools in the world, right? The problem is very simple. It's something that you can see at the undergrad level, as these subjects were. So you present them in a computer, right? Choose this. It's easy to understand. So what's up, right? So I mean, one thing you will say, look, when Mascolel is developing the theory of consumer theory, he's assuming, right, consumers, for instance, know exactly what prices they're facing. So if you are facing a graphical budget, right, then these experimenters, they imagine that consumers could perfectly infer the relative prices from the observed slope of the budget line. Do you agree with that? Do you understand what I'm saying? So essentially, in the setup of this experiment, right, they force you to choose from a budget line, but they tell you the income, but they don't tell you really the relative prices, right? They just show you the relative price. Okay. So I guess there should be some number that will give you the relative numbers. I wasn't aware that they were given the numbers. Even if they were given the numbers, it seems that it wasn't the salient part. The salient part was the graphical representation of the prices. So as opposed to Mascolel theory, if you want to be gracious with Mascolel's theory of consumer theory,
maybe,
right?
Professor, maybe it was context dependent as well. I don't know. I mean, maybe it's also they didn't have all the information, or maybe it because they had to make like 50 decisions. It's a lot, right? So
yeah. So context dependent here, I don't think is the reason. Here there is no intent or form to try to frame this thing in different ways. So I don't think that's it. I think the main issue is that true, consumers may get tired. There's 50 decision tasks, right? You may try to, you get tired of you're not gonna be truthfully choosing anyone, even if you're going to be paid to do a good job, right? So these guys, have a lot of money, these experimenters, so they give them incentives such that you can actually match way more than what a usually undergrad in Berkeley earns, so which is way above the minimum, right? So these guys basically were careful in giving enough money, and there has been other experiments where they have increased a lot of money for this kind of experiment, right? So actually to the thousands. But so the issue versus many alternatives, do people get tired and say, okay, this is an experiment, I am tired, I don't want to do it, right? So after if you take, for instance, this original data and you cut it on just the 25, half of the observations, will this be more likely to pass GARP? Yes, but this is mechanically, right? The more budgets you have, right, the more chances you have to fail any test, right? This happens with any test. The more data points you have, right, it's more likely that your test is gonna fail because your test becomes more restricted, right? But essentially, one key issue, I think, is, for instance, that what Amadi is suggesting a little bit. So are consumers truly engaged with the decision task? Are they fully attentive, right? Are they, not tired or randomizing in the last rounds? Okay. So that's all important questions, but also in a way, right? So when consumers are fully engaged, they are not distracted. They fully understand prices. So under which real life situation this happens, right? So, and also this makes you think, is our theory of consumer theory just a theory of the vacuum, right? Where consumers are living a bubble, right? And they are fully engaged with the consumer problem. The consumer problem is super easy. Prices are super understood. And then only then you can maximize, right? So clearly there is something going on, right? 17%, is a very bad rate. So, and again, so what are we modeling, right? Are we modeling ideal subjects in a bubble, right? Or are we modeling real human beings subjects to some distractions and some imperfections? So if so, right, are we really, doing a good job with our theory? And, you know, so all of these are good questions. But the good thing is that at least we have a test and we can see this number, right? And the number says is 17%. And this is a low number. So now we have to do something about it, try to process it, right? And one particular first answer that some people in real preference try to give was a little bit not satisfactory, but is very popular right now, and you have to learn it, but we're gonna criticize it a bit as well. And this is basically an approach of goodness of fit. So essentially we say, look, you take the lazy approach that all models are wrong, right? You say, look, all models are wrong. Hence, you know, it doesn't matter if it's wrong, it matters how wrong it is, right? So if you want to measure how wrong it is, you basically have to create a measure of this, right? And this is the rationality measures of performance. So the people in real preference, they basically invented the following notion. So consider a number between 0 and 1. And now I'm going to define a modified reveal preference relation that says that you are reveal prefer xt is reveal prefer to xs to the alpha degree whenever alpha times ptxt greater than or equal ptxs. So remember the definition of reveal preference before. This is equal to alpha equal to 1, right? Now here we're modulating the expenditure that of ptxt by alpha. So that means that if you are still a reveal prefer, for instance, imagine alpha is 1/2, right? And xt is still alpha reveal prefer to xs. So that means, right, that what you spend on xt was so much, right, that even if you scale it down by 1/2, you're still above ptxs. So it means that you paid so much money for xt that it has to be good, right? It has to be better than xt. So alpha is kind of creating a threshold, right? It's saying not every real preference is truthful. Only certain real preferences are truthful, and they are kind of the robust real preference, right? So, and the way to do it is basically by saying, let's scale down the expenditure that you make on any alternative by alpha. Okay, so there is an interpretation of this. And the interpretation of this is that this is essentially the amount of money you are ready to waste in order to obtain the same welfare, right? For instance, imagine that you like xt better than xs, and you could have buy xt at half the price, right? But you're buying it at double the price, but you're still reaching the same utility, right? So this alpha in the end is going to tell you, you know, the amount of wasted income that you're going to spend achieving the same income, the same utility, but you're going to be wasteful. So in other words, if you're rational, there is no waste. So rationality here means efficiency. You're going to reach the utility with a minimal expenditure, right? We know that there is this duality between utility maximization and expenditure minimization. So that means, right, that the utility maximization bundle, if you're rational, then you're going to minimize waste or expenditure. Now, if you fail to be rational, right? So that means the reveal preference relation fails GARP, like our guys in the experiment. That means that there is some waste going on. How do I measure this waste? By using this alpha. Okay. Now, how do I measure the waste? So there are many possible alphas. So in particular, notice that every data set, any data set that I have, will satisfy GARP alpha, right? So not original GARP, but GARP for the reveal preference to the alpha. For some alpha, in particular, notice that if alpha is 0, then the reveal preference relation is always empty. Empty preference relations are acyclic, so they satisfy vacuously GARP, okay? So they satisfy vacuously GARP. So that means that since this is continuous, since it always passes with 0, there can be other numbers, right? And if you're rational, this number is 1, that will satisfy the GARP. So how do you pick one number that makes sense for our measure? Well, you take the maximum alpha such that the data set satisfies GARP on the preference alpha. Okay, understood? So this means, for instance, that
Professor,
yeah.
the maximum alpha warrants me that I am trying to be more the closer possible to the rational, completely rational behavior. That is the intuition.
Yes. Yes. So like, for instance, if you have a rational person, the alpha will be equal to 1, right?
Okay. Yeah. Okay. Thank you.
Yeah. And the other extreme is alpha equal to 0. So it's someone that, you know, the real preferences are so messed up that they can never be guarded except if I kill everything, right? And of course, most numbers is going to be above 0. And then, you know, you're trying to pick the one closest to rationality, right? And then the closest you are to 1, the closest you are to rationality, okay? So then, yeah. So the critical cost efficiency index is this thing where you're taking the max alpha. So here I'm just using the SUC to be careful, right? Because it's not clear, you know, that 1 is achievable, so it might be open, right? So yeah, just to be careful in the sense that it's not a bounded set, but you know, it's not, sorry, it's not a closed set more than bounded, it's bounded. Where alpha, if there is a U that rationalizes the data, right? It amounts to checking SARP-GARP for a grid of values and so on. Okay, so this part here, let me see if I can fix it up, because I do want you to see this. So let me quickly go through the documents. I think I can fix it quickly. Yeah, I have the CCI here. Yep. Is it? Yeah. Can you see the graph? Yes.
Yeah.
Okay. So this is the same data set I described it, right? And here I'm gonna give you, this is kind of a cumulative distribution. It's a little bit flipped. This is the percentage of people that are above a given Afriad efficiency index, the CCCI. So this is a cost, basically the critical cost efficiency index. That's why it's called the CCCEI. And this is the percentage of people that are greater than or equal to a given Afriad index, right? For instance, this will be 1, which is exactly the GARP, right? So here in the upper left corner. Then, you know, the 17% of these individuals, which is the red line, pass GARP, right? So see around this is 70%, right? Now you see, right, that if I want to rationalize more people, I have to decrease the GARP. Right? So people that are about above 0.9, check out the right now, it's very close to 1, right? So you keep going, right? But where do you have the, sorry, this is the percentage of people, this is the CCCI. So this is 1, and then what is the fraction of people that are passing GARP? You go here, right? And this is 17%, okay? Now, let's say I lower the Afriad efficiency index to 0.9, okay? So 10% of wasted income. Now, you go here, you check this red line, and there is 80% of people above 80%, right? Now you move to 70%, and now there is 95, and you move to 60%, and it's 1%, is 1, right? So there is, in order for everyone to pass, you have there are people wasting 40% of the income, right? So now, again, so what is now the dotted line? Is essentially they did a simulated GARP just from random choice. So they allow uniform choice from the linear budgets, right? To pick at random. And then they are checking what will be the implied possibility of passing the Afriad efficiency index given a certain number if you come from random or zero intelligence behavior. And this is the dotted line, right? So for instance, if you want everyone to pass from the randomly generated data, it will be, the CCCI will be 30%, right? And then a little bit the idea is that this is separated from the red line, right? So that these mistakes are far from being random, okay? So the mistakes you make, yes, they take you away from rationality, but they are still not very far, right? That's the claim. Now, I want you to be critical with this. So there are some cool things about this, and there are some bad things about this. First of all, right, you know, if you are super serious about science, right, your model is wrong or right, right? There is no middle point, right? So then, you know, if your model is wrong, then you should discard it and then try to see why your model is wrong and try to improve it, right? So propose another model, okay? Here, you know, we are not ready to give up on the model, so we want to measure how bad it is, right? Kind of a diagnosis, right? So saying, is it really bad? Now, in order to do that, there are many ways to measure a model, you know, how it fits the data. If you come from metrics, what is the usual way? So it's ordinary least squares, right? So you have a prediction of the model, you have a data point, and you measure the square deviation, right? By means of the Euclidean distance. Okay. So why don't we use this here? Well, there is a main difficulty. The predictions of the model here, rationality, are set correspondences, right? So they are set predictions. And then you have data points. So then, you know, there is an issue that you have a model that has a set prediction and you have data points. Of course, there are metrics that measures the distance from points to sets, right? So you could try to use that. So people haven't done it yet, right? But that's a possibility. But the issue, as you can imagine, right, is that it's a very complex object, right? And then how do you minimize? Here, there is not really a parameter. It's only the rational preference, right? So in particular, for instance, when you fail a data set, there is no degrees of freedom, right? So you fail it, period, right? So what people are doing is trying to go back to a more familiar place. So they're saying, look, there is, this is fully non-parametric. However, we can add one parameter to it, the alpha efficiency index, the alpha, right? In order to try to make it a parametric family. So the issue is that now, you know, the GARP alpha, the R alpha is of course an empty model because there is always an alpha, 0, that will pass any data, right? So now you're in the realm of, this is not science, right? This is more like machine learning, so you can fit anything, right? So in that particular sense, you know, you are converted this model into a parametric model by means of the alpha, and this expands the model, okay? Now, when you expand a model, it'd be nice if you expand it with some reasoning, right? Here, you know, it's more about simplicity. So, you know, people try to rationalize it by calling it wasted income and so on. But the main reasoning is that the is the easiest modification to the GARP algorithm that the computer will allow, right? So essentially, you can fix an alpha, and then you can check the alpha GARP exactly as you would check in the GARP, okay? So for your problem set, essentially, if you're able to code GARP, then you can go to the same code, right? And modify the real preference relation with an alpha, right? And then you can essentially solve for each alpha in a grid and then maximize over the grid, right? So that means the interval is 0, 1. You can discretize the grid, 0.1, 0.2, 0.3, dot, 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 to 1. And then because GARP is easy to solve the GARP in each grid point, right? And then max over the grid, okay? So that's essentially why people have done it. So it's computational simplicity, okay? Agree? Yeah, so now, but again, there are many issues with this. It is not clear, for instance, why, if you are an experimenter, a scientist, you should care that a model fails in terms of wasted income, right? So wasted income is more this measure that tells you that consumers will be wasting this fraction of their income for achieving the same utility. They could have achieved the same utility being rational, hence efficient, and not wasting any income, right? But that is a measure that is kind of normative. They say people should have behaved differently. But this a little bit goes against what people do in metrics and in other fields. And usually people are trying to measure performance of models, they focus on the prediction of behavior, right? So that means you are predicting, this is the prediction of my model, and this is the data point. There is a gap here. how can I, is this far enough such that I can reject my model? So again, this has become a hot area of research. People are trying to find ways to measure how rationality departs from data. Surprise, surprise, it seems that in most data sets, there is a gap between, you know, what people do and rationality, right? And this gap seems to be significant, right? And then people are trying to understand why. So is there any questions here about especially this figure? No?
Maybe just a thought. Is there any sense of removing outliers from the data? Even in the 50 choices, like it only takes one choice to fail GARP. So maybe if you go through and get rid of people's worst choice, then all of a sudden your efficiency index would be higher throughout.
Yeah, so
that-
there is something, so there are many measures. Remember, outliers are defined within a metric, right? So you define a distance, right? And then, for instance, you have a Euclidean distance, whatever, right? Some variance, something normalized. Then you can think with that metric inside. Here, you know, one thing that sounds like what you're proposing, Severin, you know, there are many. So, but one in particular is the index that's called the Hoodman Max. So they basically have a data set of 50 observations. And then this index basically is the fraction of observations you have to drop before rationality is reestablished, right? So it's kind of an outlier approach. So again, a particular individual has a Hoodman index. So you have to drop half of the observations, right? Your Hoodman index is really bad. If you don't have to drop any observation, then you're fine. So that's a little bit like what you're suggesting, right? But there are other similar to that when you have a kind of pair observation Apred index, right? And then you can also do that. Yeah, so for instance, you can also think that you can measure the Apred index for each individual, right? And say, I'm gonna just keep the ones that are above 0.9 because they are rational, right? But again, the same thing with outliers. Is this justifiable or not? You know, same critiques apply. Yeah, so my main point is that this is a little bit again, we have a new model, right? That is described parametrically. This model happens to fail in the data. You have two roads. One is to change the model. Another is to try to find some measure of goodness of fit. And in finding the measure of goodness of fit, people haven't settled in one yet. This is the one that is the most popular, right? And it has pros and cons, right? And yeah, good point, Severin. But yeah, this is a little bit open field, right? So people don't know exactly what is the best practice here. And again, I'm just pointing out the conceptual issues, okay?
Sounds good.
Okay, so here I'm gonna describe measurement error, which is what I work on. So in particular, this is going to give you a little bit of context to what people have done with this problem, right? So if rationality fails, what's up? What are we doing here, right? Because the rest of the class is based on rationality assumption, right? So are we crazy or what, right? So the reason, you know, one of the reasons people haven't give up on rationality is that they believe, right, the current data sets we have for testing rationality are not ideal. I'll leave it what Matt suggested, right? So there are issues mainly with the lack of attention, complexity of the decision task. The decision task may not be designed in a particular way that reflects real life situations or situations of interest, right? Now, so this is the experiment you're using in your replication exercise. So this, instead of having 2 goods, has 3 goods. It's still a narrow degree of security, so it has 3 states of the world. The experiment, instead of having 90 plus subjects, has 154 individuals. And the number of choices is still 50, okay, per individual. Now, in this particular world, it turns out rationality does even worse. So if you test GARP here, only 13% of cases will pass. But what's up? So basically, in my paper with Nail, what we do is we say, look, yes, so there is obviously an issue here. Let's consider the possibility, right, that consumers are basically making 2 random mistakes. So when you make random mistakes, they are not mistakes that should be theorized, but rather clean. So you have an experiment. Imagine you are running an experiment in physics, right? And you're measuring, for instance, parabolic throws, or something that has to be tracked through precision, right? Initial velocity, final, height, length of the flight. If you have, for instance, some defective measurement device, right? Essentially, you could have some issues, right? So, for instance, your classical theory of parabolic throw won't hold up because you have some noise in the measurements of the final length of the fly and so on. So that's a little bit our idea. So what possible noises people have documented in this experiment? So in particular, there are two that are well documented. One of them is called trembling hand. So when people are choosing using a mouse, right, there is a definition of the mouse, and there is some possible mistake made by the consumer by physically pointing to something that is different, right? So there is some validation experiments where they actually try to measure this trembling hand error directly. So they give a validation exercise to the same subject in similar kind of experiment. They give a target coordinate, and they ask the consumers to point that coordinate. So here it's not about choice. So the target is given, right? So it's X, Y, it's a coordinate. The subjects have to use the mouse to go to the coordinate. Sometimes they fail, right? These mistakes, little mistakes in pointing to the true coordinate they were ordered to point, are evidence that people made mistakes using trembling hand, right? So now the magnitude of those mistakes might not be enough to represent something, right? And also, the only thing we know about those mistakes is that if you average them, then you're gonna, in average, be targeting the correct point, okay? So they are mean zero in a way, okay? So imagine you're pointing in on the budget line, you want the middle point, and people, that were ordered to point the middle point will be pointing around, right? But if you average these positions, the middle position, the average position will be just in the middle, right? That's what I'm saying. The second kind of error, which is the one we find more evidence for, is what is called trembling eye. That was our funny name. So what do we mean by that? So we mean the following. As I mentioned, in this kind of experiments that use visual interface, you have to infer the price from the budget lines, okay? You have to infer the price from the budget lines, from the budget slope. So this is a 3D experiment, right? It's even more complex. So in fact, you have to infer from the, the projection in the screen, right? There is a drawing representing the 3D budget line, right? And then you have to infer the prices. So it's even more complex. So now the same thing, right? We imagine people are guessing, the true price, but in average, the price would be equal to the true price, right? So we have some evidence here. The task that people were given in validation exercises was that they were asked to tell me, the values that they see in a particular coordinate. And then, of course, they fail. And these mistakes seems to be random. So they average to mean zero, okay? Now, with this validation data, so we say, look, let's go to this original experiment. Here, there is no validation data. We're just gonna use these two pieces of knowledge, that the average trembling hand error and the average inattention to prices error or trembling eye error is equal to 0. So the only thing we're gonna use, and this is gonna be a part of the test. So we're gonna jointly test that consumers are rational jointly with, they are facing some random errors, possibly on the trembling hand or the trembling eye, such that these errors average to 0, okay? So they are non-systematic, okay? So as you can see here, what we're doing is we're imagining that the true data, instead of being the observed data, is the observed data, sorry, is equal to the true data plus measurement error in consumption with a super C, and prices the same. The price that you observe is equal to the true price, sorry, the price that the human subject observes is equal to the true price given by the experimenter plus measurement error, right? So now the key of this is that now we cannot test individually GARP, right? Because GARP can only be tested individually because you have perfect data. So in my paper with Nael, because now we know errors average out, we have to instead use also the information across the individuals. So instead of using just the time series of each individual, right, with 50 observations, we pull them into a panel, right? The panel will contain the 154 individuals, right, in the one dimension, and 50 observations per individual, given the time dimension. So this is a panel now. So in this setup, what we do is we test whether there exists any distribution of measurement error, right? Such that given that distribution of measurement error, each individual satisfies GARP individually, and across individuals, the average measurement error in trembling hand or trembling eye will be equal to 0. So it's two requirements, right? In the time dimension, we're requiring every individual in the true data to satisfy SGARP. And in the cross section, we're requiring the average of errors across individuals to be mean 0. Okay. So doing that, we propose a new statistical test. And in fact, we conclude that the null hypothesis that every individual in this experiment is consistent with GARP, everyone, cannot be rejected at the 95% confidence level. We also find that misperception of prices seems to be the culprit of many violations of rationality. So importantly here, does this confirm rationality? Well, certainly no, right? Because you're doing a statistical test now, right? There is noise. So you know that when you don't reject a hypothesis, it doesn't mean that the hypothesis is true. What it means, of course, is that we can actually, if because our test is GARP style, so that means we're testing all possible testable conditions. So that means actually we can reverse engineer, right? Distribution of utilities such that if I maximize each utility subject to the prices, you will get back the data. So in that sense, you can rationalize in this new notion with measurement error as well the data set you observe. What we're saying, and this is the more toned down conclusion, of course, is that the theory cannot be confirmed by this exercise alone, for sure. But we say that the current evidence, for instance, coming from this kind of experiments, isn't sufficient to reject rationality, at least in the context of this simple experiment. And the main reason is, of course, that so if we're testing rationality, we have to be clear about assumptions, right? And one key assumption of the model is that people perceive prices perfectly, right? And that they pick what they want. So they pick what they meant to pick, okay? They are not picking something by random error, okay? So in summary, right, by cleaning these two types of possible noise, the evidence against rationality that seemed to be overwhelming actually disappears, right? So now, of course, we make the checks in that paper to show that our test is not trivial, right? That there are data sets that will fail this test, right? And the power of this test actually is reasonable, right? So there are, if you actually were coming, for instance, from random behavior, then even if I corrected for this trembling hand and so on, you still will fail it, okay? So this test has power. So it's not just an artifact that our new test, given less stringent, it just passes because of that. Our test is in fact very stringent because it requires that every individual in the cross-section passes. So every individual is rational, 100% of them is rational, okay? That is what makes it stringent, okay? So, however, even if it's stringent, it still passes. And the reason is that there seems to be, these guys are not totally crazy, right? Now, let's think about it, for a second. And one thing that Ahmad was saying, for instance, is that as time progresses, right, more time trials goes, right? Essentially, you may have that people are paying less attention to prices or they are picking more at random. So, these things obviously can be captured by our condition because we only require that third time trial, or imagine you are in the position 50 versus position 1 in terms of the trials. we are not putting any restrictions on the variance of the errors, right? So the errors are arbitrary. They can be growing, right, as Amat suggested. So this is perfectly compatible with that. The only thing we're requiring is that they still remain in the middle, so that these errors are truly random. So for instance, in every time period, people that get tired, some of them point to the left, some to the right, but in average, they still are unsystematically moving away. So what we should worry, and that's of course my philosophy, is that you should worry about systematic deviations. For instance, if you see people in the 50th observation, right, always leaning to the second state of the world, right, there must be something about that state of the world that is everyone making them go there. That can be like context dependence, it can be learning, right, it can be some bias for some reason, right? So that thing, systemic deviations, those are the synonymous to biases, right? So those are the things that reject a theory truly, but only random noise, right? That cannot reject a theory, right? Because these are things you have to get rid of, are a byproduct of the data collection, not of a data generating process that is systematic, right? So this is, of course, the modern approach to science, right? Most sciences, they are not tested deterministically, right? But rather a statistical version of it is tested, right? And that's what we do, especially in economics and social science, okay? So this is converting the guard into a statistical object by means of measurement error, okay? Now, is this the final word? Well, obviously not. This is a very open thing. People are still figuring out what to do, okay? So at this stage, I'm gonna give you two options, right? So I know the material is a lot, right? You still have to deal with this programming task, which is also a lot because it's not usually what you do. So at this stage, I think I will stop at this stage the class. I was planning to do some welfare and some additional topics on homothetic, but the welfare, if you read, is very short. I'm gonna do this as part of the problem set. Is have a page, and essentially, it's super simple. And what I want right now is basically to stop and take some questions about the problem set, especially about the programming part, right, that you're having. And since Fenghan, he already wrote to me that he's not going to be that helpful in this particular case because he's not that into, programming yet. So, and I said yet purposely, right? This is the time of learning to program. Yeah, but his skills are mostly theoretical, right? So I'm happy to, to at least have an hour, take some questions from you for the programming part, if any, right? Yeah, so here I'm going to stop the recording.